In the previous videos we talked about the beta oxidation. In this video we would talk about the alpha and omega oxidation, which are the other pathways of fatty acid oxidation. Although they are minor pathways as compared to the beta oxidation, but they do occur. The first point is that they both occur aerobically. They both require the presence of oxygen. The alpha oxidation occurs mainly in the brain and liver microsomes, while the omega oxidation occurs mainly in the liver microsomes only. While the omega and alpha and omega oxidation, they both do not require the initial activation of the fatty acid as it was required in the fatty acid for the fatty acid entering the beta oxidation. So in this way we would save a phosphate bond as well. The unique feature of the alpha oxidation is that its product has one carbon less as compared to its substrate. This is because of the third step, decarboxylation step, which results in the removal of the fatty acid carbon, as the carbon dioxide has the final product of the alpha oxidation would have one carbon less, while the alpha oxidation has no such decarboxylation step, so its product would have the same carbon length as compared to as its substrate has. There are three main steps in both alpha and omega oxidation. The first two are common to both alpha and omega oxidation, that is the hydroxylation step and the dehydrogenation step. First we will talk about the alpha oxidation. In alpha oxidation, the first step is the hydroxylation step, which results in the attachment of a hydroxyl group to this alpha carbon. This is catalyzed by an alpha hydroxylase enzyme which uses the ferrous iron, vitamin C and tetrahydrofluoride as cofactors. This results in the production of alpha hydroxyl fatty acid, as a hydroxyl group is attached to the alpha carbon. So therefore it is called as the alpha hydroxyl fatty acid. The second step is the dehydrogenation step, in which the hydrogen attached to this hydroxyl group and that hydrogen attached directly to the alpha carbon is removed by a dehydrogenase enzyme, and this would result in the production of a keto group. As you can see that the keto group is formed by the removal of two hydrogens, one from hydroxyl group and one from the alpha carbon. These hydrogens would reduce the NAD, the coenzyme, to NADH2, and the resultant compound will be alpha keto acid. As the keto group is on alpha carbon, so it would be alpha keto acid. The third step, which is a unique step in the alpha oxidation and due to which its product had one carbon less as its substrate as compared to its substrate, is the decarboxylation step, which results in the removal of this carboxyl group as carbon dioxide, and the keto group becomes the carboxyl group. This occurs spontaneously, no enzyme is required for this processing, and the final product of the alpha oxidation would form, that is a fatty acid having one carbon less as compared to its substrate. Now moving towards the omega oxidation, it has the same first two steps, the hydroxylation, but this time it involves the omega carbon. Omega carbon is the last carbon or the farthest away carbon from this functional group. I highlighted this. So a hydroxyl group would attack this omega carbon and would attach to it and this reaction is catalyzed by omega hydroxylase enzyme, which uses the cytochrome P450 and molecular oxygen. It would result in an omega hydroxyl fatty acid molecule. The second step is the dehydrogenation, in which this hydroxyl hydrogen and the one attached to this omega carbon would be removed by a dehydrogenase enzyme, and the resultant molecule would be an omega keto acid, as a keto group is also formed over here. And this time NADP would be used as a coenzyme, while in case of alpha oxidation, the same dehydrogenation step involves NAD. So in this case we would have an extra phosphate over here. Anyhow, NADPH2 would be formed. The product alpha keto acid would enter the next step, which is the oxidation step. In this oxidation step, what happens that by the addition of a molecular oxygen in the presence of an aldehyde enzyme, what happens that the hydrogen is attached over here, and this hydrogen becomes a hydroxyl group. As you can see that the oxygen is attached to this hydrogen. So one carboxyl group is formed at the starting point of this fatty acid molecule, and one is formed at the ending point. In simple words, one is formed over the alpha carbon or near the alpha carbon, and the other is formed on the omega carbon. So the compound would be alpha omega dicarboxylic acid. So the final product of both the alpha and omega oxidation would enter the beta oxidation, in which its further processing would occur. In my previous video of the beta oxidation, I had told you that the beta oxidation produces only acetyl groups if the entering fatty acid is even carbon, and it would produce an additional propionyl coenzyme if the entering fatty acid is odd carbon. When I was studying the whole chemistry of these alpha and omega oxidation, I noticed a point that the omega oxidation is energetically more profitable as compared to this alpha oxidation, in such a manner that let us assume that an even carbon fatty acid enters both omega oxidation and alpha oxidation spontaneously. So what would happen, that alpha oxidation would produce an odd carbon fatty acid, while omega oxidation would produce the same even carbon fatty acid. So when this even carbon and this odd carbon fatty acid would enter the beta oxidation, so in case of this odd carbon, an additional propionyl coenzyme would be produced alongside the acetyl groups, while in case of this even carbon fatty acid, all the acetyl groups would be produced. As in this case, a propionyl group is also produced, and due to this propionyl coenzyme, as it is energetically less profitable as compared to the acetyl groups, this odd carbon fatty acid would give less energy as compared to this even carbon fatty acid entering the beta oxidation. So in this way, as the alpha oxidation produces the odd carbon fatty acid, while the omega oxidation produces the same carbon fatty acid, so in this way I assume that the omega oxidation is energetically more profitable as compared to this alpha oxidation. So this was all about the alpha and omega oxidation. We have gone through their comparison, and a bit we have also given a bit touch to the beta oxidation. If you still had any question, you can comment. Stay safe. Allah Hafiz.